PAM-VCC. What is that? It's a platform for autonomous multi-vehicle communication and coordination. Imagine driving around a mountain pass, all the curvy roads, not being able to see what's around you. Imagine driving in dense fog or through a blizzard. You can't see anything. But with this system on top of your car, you can see every single other car around you within a 100-meter radius. You have 3 GPS units, all calculating the position to increase accuracy down to within 50 centimeters. We have an XP transmitter that transmits wirelessly up to 100 meters. We have the AppMega microcontroller as the brains of the operation. And we have an accelerometer and compass. All of these work together in order to create this network of vehicles in which everybody is able to communicate. In addition, we have 4 IR sensors, 2 in the front, 2 in the back, that help its localization and avoid other vehicles and obstacles that are in its path. What essentially PAM-VCC does is creates a network of cars that communicates your relative location, your direction of travel, acceleration, velocity, weight, dimensions, your height and width, and braking distance. All this information, all the other vehicles then get displayed onto a graphical user interface inside your car, which you can then see all the vehicles around you. By knowing where all the vehicles are around you, you can then prevent collisions. You know where their cars, you know where your car is, you know your velocity, your acceleration, then you can essentially just stop before that collision occurs. If you do collide into something, these vehicles, the PAM-VCC unit transmits out an emergency stop command, and all the other vehicles around you immediately come to a complete stop. We can't go from where we are right now to fully autonomous vehicles. We need something in between, and that's exactly what PAM-VCC is that stepping stone towards fully autonomous vehicle.
So we're gathering data from the IR sensors, the GPS, the accelerometer and compass, as well as sending data out onto the XP chip. Now, this is taking up a lot of our cycle time on our microprocessor, especially considering that the GPS is very slow. It only operates at around 5 Hertz, so it takes about 300 milliseconds or so to process all the data incoming from the GPS circuits. So we were really running into a limit with our AppMega. That was something we didn't think of when we first were doing our design considerations. If we redid this project, we'd probably go with multiple microcontrollers for each sensor. So we'd have one microcontroller to gather the data continuously from the GPS, and then after some parsing, forward it to the central brain for transmission out onto the XP chip. Another thing we could do possibly is implement some kind of real-time operating system onto the AppMega, but the multiple microcontroller solution would also work very well. Another design consideration we ran up against is we chose a chip that had a combined accelerometer and compass. And this gave us some difficulties later when we were attempting to calibrate it because of the influence of its magnetic field. It varies greatly from place to place. It also varies when the vehicle moves because it uses the acceleration of gravity to figure out which way is down. If we had gotten a unit such as an IMU, an inertial measurement unit, we would have had an embedded gyroscope that would have helped us cancel out the movement of the vehicle and get a more accurate directional reading to calibrate our compasses against.
The last design consideration we had to take into account is we had no means of transmitting our velocity or position that we traveled to the surrounding vehicles. We had to incorporate a wheel encoder so that we could gather our position and our velocity and then send it to the surrounding vehicles. This allowed for our collision mitigation that we'd implement later. Due to our limited budget, we had to use 3 GPS units opposed to an ultra-wideband transceiver. Ideally, we would use an ultra-wideband transceiver, which could send signal directly to other surrounding vehicles, taking the lag of the satellite signals out of the equation. We also had trouble with the IR sensors. We knew that they're going to be trouble in sunlight, but again, due to budget, we had to compromise. As you can see from our top level block diagram, our power supply is going to be an external power supply that supplies the rest of the system. It will have 8 AA batteries that supply a 12 volt input to our switching IC, which will be bucked down to 3 separate rails. We'll have a 3.3 volt rail, a 5 volt rail, as well as a 9 volt rail. The 3.3 volt rail will supply voltage to the GPS and accelerometers. The 5-volt rail will supply the XB UART expander, which in turn powers the XB. The wheel encoder, the infrared sensors, and our 9-volt rail will be solely responsible for powering our ATmega microprocessor.
The accelerometer block is actually a combined accelerometer and compass. It takes in readings from the Earth's magnetic field as well as measures the external acceleration forces applied to it. It then communicates to the ATmega microprocessor through a I2C protocol. The microprocessor parses this data and sends it through a UART connection at 57600 baud to the XB unit. The XB unit communicates this to other surrounding XBs as well as an XB attached to our external interface computer. This external interface of our laptop runs a Python program which takes in all the incoming data from the microprocessor and draws a graphical picture of the vehicles based off the sensor data that it receives.
For the location code block, we implemented 3 GPS receivers. For our actual conceptual test, we simply used the average of the 3. Ideally, we would create a Gaussian distribution and based off all 3 GPSs, find the highest probable location. The collision mitigation code block essentially transmits a stop command wirelessly and broadcasts this stop command to all PAM-VCC vehicles within the area. This was then received by the other vehicle, and then a collision is what is considered detected. At a point when a collision is detected, the user will lose control of the vehicle, and the vehicle itself will take over and stop. And in addition, it will relay this stop command out to other PAM-VCC vehicles. So every single vehicle around the collision, as soon as a collision is detected, will come to a complete stop. The wheel encoder block is an optical wheel encoder connected to the front right wheel, and it measures the revolutions. There are 120 ticks per revolution, and so we calculate this in terms of velocity of centimeters per second.
Communication amongst the vehicles. The second part will connect it to the first. It'll trigger an IR interrupt telling it to stop. It will also forward a signal to the other vehicle telling it to do the same thing.
Here we go.
And here's a demonstration of our IR sensors triggering interrupt so that it doesn't collide with the wall. And you'll see that I never let go of the trigger.
Very nice.
We're going to show you our collision mitigation response to a vehicle trying to collide with another wall. This vehicle will try to stop by initiating its braking sequence, which is actually a reverse. First, it must be spinning forward. You'll note that there's no interrupt happening. And that was triggered by that guy trying to collide with the wall.
Okay, helpful hints for next year. When you're designing your code, if you have any sort of flow of control, draw out the block diagrams or state machines or timing diagrams or anything. Make sure that you understand completely how the code is going to progress from one state to the other so you don't run into issues when you're programming your protocols at the last minute before checkoffs.
The same thing goes with the hardware. You need to make sure that all your hardware is functional independently before you start connecting it together. Do small stages before integrating the whole stuff together. Everything must work individually.
And as much as you may not like to hear this, you need to use your winter term. You need to show up and you need to work with your team over the break. Also, you need to be aware of caffeine addiction and you need to keep your sense of humor.
Yes.
1 minute.
Nailed it!
Nailed. So they asked things like, what was one of your biggest difficulties?
And what did you say?
You sound like an interviewer, like for a biography. And what did you say? How did you feel? How did it make you feel?
And?
I was angry.